Imagine a normal day at Savitribai Phule Pune University campus. Classes are going on smoothly. Suddenly, the electricity goes off in one of the building. Immediately, generators start. The local guards are responding, and the class continues. Nobody exactly planned this exact moment, but we can see the system was ready. A computer works in the same way. It normally executes programs step by step, but real life events keep happening around it. A key is pressed, internet data arrives, a mistake happens inside the program. The computer must stop what it is doing for a moment and handle the situation properly and then continue. Interrupts and exceptions are the emergency response system of a computer. They help the CPU react to the unexpected events without panicking, without losing the data, even without crashing the entire system. So let us understand what exactly these interrupts and exceptions are. Think about you are standing in a queue at Pune station, Pune railway station, ticket counter, probably. You are talking to a friend and suddenly your phone rings. You pause the conversation and attend the call and then continue talking. That phone call is like an interrupt. Now imagine you are submitting an online form, say on say Maharashtra government portal, or let us say an examination form that you are submitting for your examinations. And what happened is like you entered an invalid say number. Let us say your PRN, or probably if it is expecting some service where you are applying for at my is through my Seva Kendra, or probably Aple Sarkar portal of Maharashtra government, and you are expected to put your Aadhaar number and you put it invalid way. The website immediately will be showing you an error, and that error comes from inside the system, and that is called as an exception. An interrupt comes from outside the CPU. For example, you can say keyboard press, mouse clicks, network messages, timer ticks. An exception happens inside the CPU itself. For example, like dividing by zero, accessing wrong memory area. If at all there is an invalid instruction given, both of these situations pause the CPU for a short time so that the problem or request is handled correctly. Now let us try to understand how the CPU knows that something happened, like how the trap, exceptions, hardware interrupts, and software interrupts are. Some interruptions are planned. When a student application wants to open a file, let us say in Ubuntu lab system at our department, the programs cannot directly access the disk. It politely asks the operating system for help, and this planned request is called as trap. It safely moves the CPU from user mode to kernel mode. Now, some interruptions are accidental. Let us take an example. If a program tries to divide a number by zero during the execution, the CPU immediately notices something wrong, and this is an exception. Now, some of the other examples are like overflow, invalid instruction, and we talked about a page fault earlier. Further, some interruptions come from the hardware. For example, when you click a mouse in the computer lab, when a pen drive is inserted, when data comes from Wi-Fi hardware sends a signal, and these are hardware interrupts. And some interruptions come from the software. Programs use them to request service or to communicate. For example, let us say you are writing a C program, and in C program you want to make use of printf to print a message. Now this would be through the program that you are passing, and that's what is a software interrupt. The CPU clearly knows the source, and according to that it reacts. Now how the CPU will handle these surprises? The CPU behaves like a very disciplined government officer. First, it finishes the current instruction, just like a clerk finishing signing one file before picking the next one. Second, it saves its position. All important details like registers and program counter are stored safely. And this is like keeping a bookmark in a book. Third, it switches to kernel mode. And this is similar to when only senior officers are allowed to take control during the emergencies. And fourth, it runs the correct handler. The interrupt service routine handles this issue. After finishing everything is restored and the program continues exactly from where it stopped. No confusion, no loss of work. Now, who fixes the interrupts? Let us meet the interrupt service routines. The real hero behind every interrupt is the interrupt service routine, also known as ISR. An ISR is a very simple and very fast function. Its job is not to do everything, but its job is to act quickly and wisely. Think of a Pune traffic police at, say, University main gate, University Circle. When the traffic builds up, they quickly manage signals and clear the road. They do not build new roads there abruptly. They just handle the moment. An ISR, that is interrupt service routine, works in a special mode. It talks directly to hardware. It finishes very fast. It handles urgent tasks and pushes heavy work for later. Let us take example from Ubuntu. When you press a key on the keyboard interrupt service routine runs. It reads the key code, stores it in a buffer, and informs the operating system. Then applications like terminal or browser read it. The single key press involves hardware. ISR, your kernel, operating system kernel, and the application work, these all work together smoothly. Now let us try to understand what Windows does when its life gets interrupted. Windows keeps a detailed interrupt table. This table acts like a directory in a government office. For every problem, it knows exactly which officer should handle this. For example, a mouse movement or a disk activity, even the network data, all generate the hardware interrupts. Windows immediately runs a write routine. If a program makes a serious mistake, Windows shows an error message. If the situation is very serious, the famous blue screen appears, and that is Windows saying the system cannot safely continue. Hardware companies also write device drivers. These drivers include their own routines so that Windows can understand how to talk with, say, printers, scanners, networks, network cards, graphics cards, and so on. Now, when we talked about Windows, let us try to see the similar thing with respect to Ubuntu. Ubuntu distribution from Linux also maintains an interrupt table inside the kernel. Every interrupt number is linked to a handler. When hardware sends a signal, kernel interrupt handlers run immediately. And to achieve this, Linux uses system calls for daily work. Opening a file, reading data, writing output. Programs use instructions like INT instruction or syscall instruction for 32-bit and 64-bit respectively to ask the kernel for the help. Linux also uses signals. If a program causes a segmentation fault, a signal is sent. The program can catch it, clean up, and exit safely instead of crashing everything. And this design is why Linux servers run reliably for months, for example, in Maharashtra government data centers. And almost like mail servers are mostly on Linux servers only. Now, let us understand how to create these ISRs. Writing an ISR is like handling sensitive government data. First, save the CPU state. Every important value must be stored before you are doing anything. Secondly, keep it short. Only urgent work is allowed. Long tasks are sent elsewhere. You have not too much worry about long tasks. Third, avoid clashes. Locks, temporary disabling of interrupts prevent two routines from touching the same data. And fourth, test carefully. The interrupt service routines must be tested many times. A small mistake can freeze the entire system. And that is why kernel programming is done with extreme care. Now let us understand why the interrupts are silent heroes of computing. As we have understood now, interrupts allow fast reaction. The system does not waste time checking devices again and again and again. They provide safety from the errors. Exceptions stop mistakes from spreading and damaging the data. They are important for all systems. You talk about multitasking, you talk about device handling, networking, everything depends on interrupts. They are valuable, like it is said, like they are valuable for careers too. Anyone interested in operating systems, device drivers, embedded systems, or even system debugging must understand the interrupts deeply, even if you want to be a system programmer at the later stage. Interrupts quickly work in the background, keeping computers stable, responsive, and reliable every single second. And that's what these interrupt things are.